This is the first of two videos about one-dimensional motion and graphing. When you're given a graph of position versus time for a particle or an object, you should be able to imagine what that motion looks like, and then translate that understanding into plots of velocity versus time and acceleration versus time. In this video, I'm going to show you a couple of examples about how to do that conceptually, and then I'm going to make a connection to calculus and derivatives at the end. Here's the first example. Let's imagine the plot of position versus time for an object moving along a straight line, and let's imagine the straight line is here. What does the motion look like? Looking at the position versus time plot, the object starts at a location that's not quite at the origin. You can see from the plot that the object moves away from the origin, stops, moves back, and so on. So the motion looks something like this. Goes up, goes down, crosses the origin, up again, and down. By the way, I set up the line so that it would be vertical, making it easier to see the connection between the plot and the motion. But there's no reason that the line has to be oriented this way. Here's that same motion, but directed horizontally. The plot of position versus time is exactly the same. And you can put the line at an angle too. It doesn't change the plot of position versus time. Now that we have established what this motion looks like, let's sketch a plot of instantaneous velocity versus time. A good way to start this process is to find spots on the position versus time plot where the slope is equal to 0. The instantaneous velocity is equal to 0 at those moments, so the velocity versus time plot has to include these zeros. Once you have zeros located, it is easier to get a sense for what happens in between. The dotted lines carve out natural zones, which I'll label 1, 2, 3, and 4. I'm going to fill in the velocity versus time plot one zone at a time. In the first zone, the slope of position versus time is initially positive, corresponding to a positive velocity, and it gradually decreases to 0. In zone 2, the slope of position versus time is 0 at the beginning and the end of the interval, and otherwise it is negative. In zone 3, the thing is turned around and is moving in the positive direction again. There are a variety of slopes to the position versus time plot, with the steepest slope somewhere in the middle and zeros at the endpoints. Finally, in zone 4, the velocity is negative again with a 0 at the left endpoint. It is difficult to say how the very ending of the plot should go, but the steepest part of position versus time in zone 4 appears to happen before the very end of the plot, so it does look like velocity versus time should come back up right near the end there. The sketch of instantaneous acceleration versus time goes much the same way. Remember that instantaneous acceleration may be found from the slope of the velocity versus time plot. Let's start by finding spots in the velocity versus time plot where the slope is equal to 0. The instantaneous acceleration is equal to 0 at these moments, so these zeros need to be on the acceleration versus time plot. With zeros located, I'll mark off new zones and think about one zone at a time. In zone 1, the slope of velocity versus time is negative aside from the endpoints, with the steepest part occurring in the middle somewhere. In zone 2, the slope of the velocity versus time plot is positive aside from the endpoints, with the steepest part again occurring somewhere in the middle. In zone 3, we're back to something like zone 1, although the slopes are not quite as steep on the velocity versus time plot as they were in zone 1. Finally, in zone 4, the slope of velocity versus time becomes positive again. Let's take a look at one more example. This one is shorter, but arguably quite a bit more important, so stay with me. Here's a new plot of position versus time, and this one is an inverted parabola. This is an important plot because this kind of motion is quite common. Any time an object is projected vertically, without air resistance of course, the position versus time plot will look like this. You can also get a plot like this if a bead slides on a frictionless wire or a block slides on a frictionless ramp. Let's generate the velocity versus time plot for this motion. Following the same method as the previous example, let's identify the places on the position versus time plot where the instantaneous velocity is 0. There happens to be only one spot, and we know that this has to be a 0 on the velocity versus time plot. So I'll just have two regions to consider this time, region 1 and region 2. In region 1, the slope is positive at time 0, and it decreases to 0 at the end of the interval. To the right of the dotted line, the velocity begins at 0 and becomes increasingly negative until the end of the interval. You might wonder how I know that the velocity versus time plot has to be a straight line. The truth is that the easiest way to show that the velocity versus time plot is a straight line is to take a derivative using calculus, and I'll have more to say about that in a minute. Finally, how about acceleration? Velocity versus time is a straight line with the same negative slope everywhere, so the acceleration versus time plot is rather boring. All of these examples have been conceptual. If you happen to have the equation for position versus time, things are a lot easier. Here's an equation that could work for the bead on the wire I showed you a moment ago. X of t is equal to minus t squared plus 4t. Velocity is the derivative of x with respect to time, so velocity is equal to minus 2t plus 4. Notice that this equation has the form of a straight line, so there is the evidence that this graph really should be linear. Finally, to find acceleration versus time, take the derivative again, and acceleration is equal to negative 2. Notice that this is a constant function, and it's negative, which matches the horizontal line we drew previously. By the way, if you're in calculus but haven't yet learned to take a derivative, you could look up the power rule to see how to do derivatives on polynomials. It's worth it to know how to do the operation even before you learn the details of differentiation. Also, if you want to try one more example, try plotting x of t is equal to negative 1/4 times the quantity x minus 2.5 to the fourth plus 9. This odd little equation produces a position versus time plot that looks quite a lot like the last example. But when you take derivatives to find velocity and acceleration versus time, you'll find much more interesting shapes as compared to the last example, and the velocity is most definitely not a straight line. If you want to see more on graphing, check out the next video, where I will turn things around and show you how to determine change in velocity from an acceleration versus time plot and displacement from a velocity versus time plot.